how a pile of sand gets turned into the smartphone in your pocket? Well, it all comes down to one tiny, absolutely essential component. Today, we're going to pull back the curtain on that fundamental building block of all modern electronics, the PN junction diode.
All right, so here's the game plan. We're going to start with the basic materials, then dig into the physics that makes them tick. After that, we'll see how we can actually hack them to do what we want, and finally, we'll put it all together to build our device and control electricity itself.
Okay, first things first. We need to get to know the three main players in the electronics game. And really, they're all defined by one super simple idea: how easily they let electricity flow through them.
So, on one side, you've got your conductors, like copper. Just think of them as a massive 8-lane superhighway where electricity can just zoom along no problem. Then, on the complete other end of the spectrum, you have insulators. Think the rubber on a power cord. They're a total dead end, a complete roadblock. Nothing gets through.
But the really interesting stuff happens right in the middle. It's not a highway, it's not a roadblock, it's something else entirely. This is the semiconductor. Materials like silicon are the real stars of our show, because we can tweak and control their properties with incredible precision. So what's the secret sauce here? Why are these materials so different? Well, to get that, we need to zoom in and look at the physics of their electrons. And it all boils down to this one concept called the energy gap.
Okay, imagine it like this. Every electron has a home base. We call it the valence band, where it's kind of just chilling, bound to its atom. Now, to get any work done, to create a current, it has to get a jolt of energy and leap up to the free-to-move level, the conduction band. And that gap between home base and the free-to-move level, that's the energy gap. It's the price of admission.
And right here, this is the key difference. For an insulator, that energy gap is just massive. It's like a giant canyon. It's almost impossible for an electron to make that jump. But for a conductor, there is no gap. The home band and the free-to-move band actually overlap. So electrons can just wander around freely with almost zero effort.
And here we have our hero, the semiconductor, sitting right in that Goldilocks zone. It has a small, totally manageable gap. It's not zero, but it's not a canyon either. It's just right. And that perfect little gap is exactly what we need to start manipulating things.
So if we know that gap is the key, how do we mess with it? Well, this is where things get really, really clever. We can literally hack the semiconductor by sprinkling in a few specific impurities. It's a process called doping, and it totally changes the rules of the game.
We start with a crystal of super pure silicon. I mean, it's a perfect orderly structure. But in this state, it's actually not that useful. All its electrons are locked up tight in bonds with their neighbors, which makes it a pretty crummy conductor.
And now we start doping. And we can go in two different directions. On one hand, we can add impurities that have an extra electron that doesn't fit into the bonds. This gives us what we call N-type, or negative type material. Or we can add impurities that are missing an electron, creating these little empty spots, or holes. And that gives us P-type, or positive type material.
So here's the big takeaway. By just swapping out a tiny fraction of the silicon atoms, we can either create a free electron that's just itching to move around, or we can create a vacant hole that basically acts like a positive charge, just waiting for an electron to fall into it. We've literally created electrical charge carriers on demand. Okay, now for the part